A cell phone without the connection is really useless. So it's key that we have a connection that enables the great science that we get back. We want to make sure that we are also, constantly connected to the satellites to provide the safety for astronauts when they're in space. We want the ISS, the International Space Station we support. We ensure that they have that connection back to the humans, a human voice and a human person who can help them if they have problems. The same will be true for the moon. When we go back to the moon for the Artemis program, we want to make sure the astronauts there have that safety where they have that connection back. And communications is key in enabling all of that. With the organization I work in, the Space Communication Navigation Program, we do deal with most use cases of NASA. And a lot of use cases of NASA can include let's monitor the oceans, let's monitor the plankton, right? But also let's monitor the universe. And so when we talk about extreme case where we have a lower orbit satellite that's just beaming down and monitoring the ocean and sea levels and the plankton, we communicate to those fairly easily using either our geosynchronous communications relay satellites, where we're just talking to them constantly through those satellites, through ground stations. But when we talk about things like Voyager 1 and 2, which are way out there, about 15 billion miles out there in space, flying into interstellar space, past our heading out of our solar system, which is a 18-hour one-way light time to the system. So you can imagine we're talking to a spacecraft that you can say hello. It doesn't receive that hello until 18 hours later, and you won't get a reply back until another 18 hours. So you talk about 36 hours before you know if it received your message or not. All enabled by our large aperture antennas, communication standards, some that were developed many years ago but are still applicable to today, using a technology of today to decode signals to still communicate with it.
SCAN is a crucial function within the agency that serves everyone. So, for example, SCAN has two major, well, let's call them two networks. There's a near space network, which is stuff between, say, the surface of the Earth and out to the moon, pretty much. That's near space. And then anything that's 2 million kilometers away from the surface of the Earth is called deep space. So there are two networks that support, there are two subnets that support near space, and that is ground stations that everyone thinks of, antennas. And then there's the relays, the TEDRA system, and that supported shuttle. It still supports space station. And these are spacecraft that are essentially in geosynchronous orbit. And then there's the deep space networks that have really big antennas, 70-meter antennas. For example, they're the ones that listen to Voyager. They're the ones that get the imaging back from Mars, things like that. If you don't talk to a spacecraft, it literally is space junk, right? So I can launch a brick into space, but the brick doesn't talk, right? So there's two aspects to this, all of which requires planning, and it involves both spectrum and then a technology solution as well, of which spectrum is incorporated. So it requires at the most fundamental level, it requires a receiver on the ground and a transmitter on the ground, and then a receiver and a transmitter on the spacecraft. And they both have to talk the same frequency, and they both have to be able to talk in the same modes. So it turns out that it isn't just simply like kind of turning on your radio. You actually have to encode the data to make it come down the most efficiently, right? So there is encoding schemes that are done. There's an inordinate amount of testing to make sure that that handshake occurs correctly. The other thing you have to realize is that when a spacecraft is going around the Earth, either in a polar orbit or an equatorial orbit, it's going about 1,000 miles an hour. So from the time that you want to be able to communicate with the spacecraft to the time that you can no longer communicate with the spacecraft is less than 10 minutes. Depending on the amount of data you need to move will determine the frequency that you use. A higher frequency will allow you to drop more data quickly. So in that 10-minute window, for example, if I only have a little bit of data, I could use an S-band frequency and of 5 megahertz bandwidth, and I can drop down a whole bunch of data that I need. All right, if I'm dropping gigabytes in that 10 minutes, that 10 minutes of sweep I can't do that in S-band. That would take 20 or 30 walk-ups like that. So that's why I go to a higher frequency like Ka band.
Yeah, part of the space communications and navigation program, our real focus is the connection piece. So we are similar to something like AT&T or Verizon, where we provide those cell phone towers and that connection. We do advise the users. In this case, the users would be the satellites, the James Webbs, the Hubbles, the ISS, where they have radio systems on their platforms, their satellites that connect back to the ground network, our deep space network, or our near space network. But we don't always provide the actual device. And so we work with the mission so they can work on the device. And again, analogy to the cell phones, like AT&T doesn't provide you a cell phone. You get that from, Samsung or Apple, but they have to connect to a network. And that's the key to ensuring that that device that they use connects to a network. And so we work with them to make sure we have standards. We actually work internationally with the standards groups to ensure there's interoperability, because what we want is that a satellite can go anywhere in the world and have a connection. And so we promote interoperability. So NASA can work with ESA or European Space Agency satellites, and they can vice versa work with our systems as well. Also, the Japanese Space Agency, again, another partnership we have with communications, ensuring we have interoperability. The Deep Space Network has about 14 apertures or 14 antennas around the globe. There's one at Goldstone in California. There's Madrid in Spain and Canberra, Australia. And so we use those global footprint. So as the Earth moves, we can constantly see the sky or see Mars or see the moon. And so since we only have 14 antennas, about roughly four each site, we're building some more. There's some that are going to be retired, but the total count is 14 at this moment. And so what we want to do is make sure that when James Webb's in sight, we also can communicate to Mars. We can communicate to other antennas. And so to make our systems as efficient as possible, we're using that multiple spacecraft per aperture, sometimes called multiple spacecraft per antenna. That allows us to talk to multiple spacecraft, as the name says, with each antenna. So ConOps, or concept that you can think about, is Mars. Because Mars is so far away, you can see more of Mars in the beam width of the antenna, especially at 34-meter. You can see more of it. And so what that allows us to do is to not only see one signal and talk to one vehicle, we can talk to multiple vehicles or multiple rovers on the surface. And so right now there's the Perseverance rover. There's also the Mars Reconnaissance Orbiter. There's Trace Gas Orbiter in Mars. And so let's say we want to talk to all of them. And it's possible now because we can see usually the orbiter plus the rover. And so instead of having one antenna dedicated to the rover, one antenna dedicated to the orbiter, we could use one antenna and receive both those signals and decode both those channels down to talk to and process both assets on the surface. When we talk about having more assets in Mars and human exploration in the late 2030s, when there's humans, there's rovers, there's orbiters, what we want to do is make sure that we can talk to all of them at the same time and make sure that we have that connection and being efficient with our signals. And efficiency, I will always hit on this part. We have to be efficient. These are lots of investment of taxpayer dollars. It's our job to be efficient with that.
Yeah, so for a typical launch, there's multi components that are utilized. Well, one is the launch vehicle, and then you've got the payloads, which are typically satellites. And each one of these, different components, the launch vehicle has maybe up to three or four different frequencies that they utilize. For example, I know that SpaceX on their Falcon 9 utilizes up to 8 frequencies because each one of those boosters, the reusable boosters, are operating their own frequencies. And with today's technologies, there's a lot of demand for live stream video, high definition video. So there's a channel dedicated for that. But once that launch vehicle is in out of the Earth's atmosphere, then it deploys its payload, a satellite. So along with on that satellite, there could be a multitude of different types of RF technologies on there. communications, there's telemetry tracking and control. It's called TT&C that helps control the aircraft or the spacecraft. But then you've got additional payloads that are on the satellite itself. For example, sensors. It could be Earth observing sensors that are looking down at the Earth and measuring the water vapor content, in the atmosphere. So that's a receiver only. But then that data needs to come back down to the Earth somehow. And it's on a different communications link. It's called the data link. A couple other components of the satellite itself is one, GPS. And then sometimes there are some additional for navigation. So NASA utilizes a bunch of different frequencies for communications. For our near space network and deep space networks, we utilize frequencies in the S band, which is typically in the 2200 to 2300 frequency band range. And then in the X band, in the 7 or 8 gigahertz range. The KU band is around 14 gigahertz. In the KA band, it's in the 25 to 37 and the 40 gigahertz ranges.
S-band, I will say, has been a legacy use for NASA from a standpoint of emergencies and just our general health and safety of our spacecraft. A lot of times they'll switch from a high gain antenna to an omni. So they're just blasting out, we need help, we're tumbling. And so we're able to capture that signal with our large apertures and then send a powerful signal up to it to say, stop tumbling or fire a thruster. We promote higher frequencies because if you think about the fixed assets that we have, the apertures, the actual antenna systems we have, it's not an infinite number. Now we drive around, you see tons of cell phone towers, tons. We do not have hundreds or thousands of towers or antennas. We have a fixed number. So we want to be efficient in our use of those fixed assets. So we promote radio systems that use high efficiency. They use high bandwidth, they use high frequencies because they're getting more data in less time. It's hard to imagine where the world will be in 10 years, where it will be in 20 years, what kind of spectrum policy we'll need in 20 years. No one could imagine. I can only, just think 20 years ago with cell phones. You would never think 5G. I wouldn't think I'd be watching a video, a 4K video on my phone, walking around or on a train, much less, just multiple cell phone towers. And you would never even imagine that 20 years ago. So put ourselves in a position in 2024. In 2044, what will we be doing? What will everybody need from a communication standpoint? It could be out of this world. It could be quantum communications. Who knows? But it's important that we remember that we'll always need a communication. No matter what form it takes, there will always be a need for communications and a connection. For me, I came to NASA really wanting to see how I can support human and science exploration. And then realizing I could be in communications definitely amplified that. Some folks will work on a mission and they'll work on one mission almost their entire career. That's great. That is awesome. Working on a mission and really just diving in, getting the science, working on that spacecraft, ensure it launches. That's great to do that. But with communications, I realized I'm able to support all the missions. We support over 100 missions daily.